Welcome to the second part of our econometrics classes. Now, in the previous class we have discussed about the need of econometrics. What is the importance of econometrics? What is the problem statement that it tries to solve? And we have also discussed about the OLS estimation. We have estimated the value of the parameters by the help of a process that is called ordinary least square estimate or OLS estimate. Okay, you may watch that video also. So now here I'm going to discuss about the concepts of classical linear regression model. Well, to be very precise, classical linear regression model is a very interesting topic. And classical linear regression model, if you talk about classical linear regression model, then it is very appropriate in real life scenarios also. You will be able to find out many applications of classical linear regression model if you try to find out. Now, what is a classical linear regression model? When I am talking about classical linear regression model, then what is actually a classical linear regression model? So, here we are going to read 10 assumptions, and if any model follows these 10 assumptions, then that model can be termed as classical linear regression model. What have I said? I said that here we are going to read 10 assumptions one by one, and if any model accepts or follows these 10 particular assumptions, then that model can be termed as classical linear regression model. What are those assumptions? Let us start one by one. The first assumption tells us that the regression model is basically the model which is given here also. You can also take the example of this model which is written in the below. Yi equals to beta 1 plus beta 2 xi plus ui. What is yi? It is a dependent variable. What is xi? It is a independent variable. And what is ui? It is a random error. And beta 1 and beta 2 is the parameters. Beta 1 is the y-intercept, beta 2 is the x slope, right? So we have discussed about this equation and about the concepts of this different meaning of these terms in the previous video. So I am not going to elaborate that for now. But the first assumption is telling us that the regression model is linear in terms of parameter. What does it mean? It tells us that as you can see, how can we check that whether our regression model is linear or not? Now here it is telling that regression model has to be linear in terms of parameter. When you have to check that the regression model is linear in terms of parameter or not, you have to do partial derivative of the dependent variable with respect to the independent variable. Okay, if I do that, let me show you. I hope it is done here. Yes. If we do partial derivative of the dependent variable with respect to the parameters, what are the parameters? Parameters are beta 0 or beta 1, or you may take beta 1 and beta 2. Denotations doesn't matter absolute at all. So if I take the partial derivative of the dependent variable with respect to the parameters one by one, at first with respect to the parameter beta 0, then what am I getting? I am getting only xi. If I take the partial derivative of the dependent variable yi with respect to beta 0, I am going to get 1 only. If I am going to take the partial derivative of yi with respect to beta 1, I am going to get xi only. Am I getting any parameter back? Am I getting any parameter back or not? Well, the answer will be no. No. When we are doing partial derivative of the dependent variable with respect to the parameters, in this form of equation where yi equals to beta 0 plus beta 1 xi, we are not getting any parameters back. When we are doing the partial derivative, in the result we are not getting any parameter, right? So when this is happening, that we are doing partial derivative of the dependent variables with respect to the parameters and we are not getting any parameter back, then we can say that our regression equation, that is yi equals to beta 0 plus beta 1 xi, is linear in terms of parameter. There is another way to explain it, and that explanation is also very easy, but mathematical explanation will be always this: we have to take the help of partial derivatives. Another easy explanation is that the power of the parameters is 1. If the power of the parameters is 1, that means that is linear in terms of parameter, or regression equation is linear in terms of parameter. Here beta 0 and beta 1 both have the power of 1, so that means our regression equation is linear in terms of parameter. Okay. Now I can show it by some other ways also, which I have discovered here. That is, let me also tell that there is another point given here, but the regression equation can be linear or non-linear also in terms of variable. That means whether my regression equation is being linear or non-linear in terms of variable, it doesn't matter at all. Just we have to focus on the parameters. It should be linear in terms of parameter. If you are interested what is linearity in terms of variable, then you can see these concepts that as x increases by 1 unit, y is increasing by 2 units, and that is a constant change in y. Whenever x is increasing by 1 unit, whenever x is increasing by 1 unit, y is increasing by 2 units. So that means the change in y is constant due to change in x. So that will give me a linear graph if I plot it. As you can see, when I am plotting the points, I am getting a linear graph. So that's why we are calling it a linear function. Now, even if we take x square, then it can't be said as linear, because whenever it is x square, whenever you will change x by 1 unit, now y will not change by the same amount of unit anymore. Take this example, y equals to 6 plus 2x square. When x equals to 1, y equals to 8. When x equals to 2, y equals to 14. That means when x increases by 1 unit, y has increased by 6 units. But when x has increased by 2 to 3, that is only 1 unit, y has increased by 10 units. So that means if you plot it now, it will not give you a linear function. So that is non-linearity in terms of variable. You can easily understand it by seeing the power of the independent variable. If independent variable is having the power 2 or 3 or 4 or more than 1, then that means it is non-linear. And if the independent variable is having the power of 1 only, then that is linear. Okay, you can do the partial derivative with respect to the independent variable also to find out whether your regression equation is linear in terms of variable or not. If you doesn't get the independent variable back, then it is linear. Let me give an example here. Suppose this case. No, this is not the case. Suppose, let me go to the page 1 at first. Suppose in this case, y equals to a plus bx. If you do the partial derivative of this equation with respect to the independent variable x, what will you get? You will get b back, right? And that means you are not getting the independent variable back, right? So whenever you are doing the partial derivative of the dependent variable with respect to independent variable and not getting the independent variable back, that means it is linear in terms of variable. And if you are doing the partial derivative with respect to the independent variable and you are getting the independent variable back, that means it is not linear in terms of variable. We can take the example of y equals to a plus bx square. If you do the partial derivative of y with respect to x, you will get the answer 2x. dy dx will be equal to 2x. So you are getting the independent variable back. It is not being removed completely. So that means it is not linear in terms of variable. So here we have learned two concepts. One is linearity in terms of variable, another one is linearity in terms of parameter. But in classical linear regression model, what assumption has to be satisfied? The assumption is that the model has to be linear in terms of parameter. But in terms of variable, it can be linear as well, it can be non-linear as well, doesn't even matter. Okay. Now we are leading to the next assumption. Yes. This is the next assumption. X values are fixed in repeated samplings. X values are fixed means that suppose there are 3 income groups. First income group is basically are of those families in which the first income group is basically of those families who have the income of $80. Second income group is of those families who are having the income of $100, and third income group is of those families who are having the income of $120. Now there are 5 families in the first income group, there are 5 families in the second income group, and there are 5 families in the third income group. Now as you can see on the what is y? Y is basically our dependent variable in the equation. What is x? It is our independent variable as far we know. Now y is denoting weekly consumption expenditure, x is denoting family income. So in case of first income group, that is of those people or of those families who are having the family income of $80, and what are their weekly consumption expenditures? The first family is consuming $55, the second family 60, 65, 70 and 75. Next group is the group of the families who are having the family income of $100. What are their weekly consumption expenditures? Their weekly consumption expenditures for the sixth family is $79. For the seventh family is $84. In this way we can just bring it on, right? So here x values are fixed, right? How? For the first income group, x value was fixed. X value was $80, right? But the y values were different. Income was fixed, that was $80 for the first income group, but the y values or the consumption expenditure values were different. For one family it was 55, for one family it was 60, for one family it was 75 and all that, right? So that is what the second assumption says, that x values are fixed in repeated sampling. Repeated sampling means x value is not always fixed. Family income is fixed, that is 80 is fixed, but for only those 5 samples. Again, or only for those 5 y values. Again, 100 is the x value which is fixed, but only for those next 5 values or next 5 y values. So we are saying here that x values are fixed in repeated sampling. Okay, and if you try to calculate the expectation of y given on x, now what does it mean? If you calculate the total consumption expenditure of all the families below the income of the income of $80, then their total will be $325. Now expectation of y given on x, what do you tell it? It is also called conditional expectation. What do you mean by conditional expectation? Well, here I have divided 325 by 5, so that is giving me the mean of 65. Now this mean can be represented as expectation of y, right? But why am I writing it as expectation of y given on x? What does it mean? Mean can be denoted as expectation of y. That is very simple, we know that, right? But we are writing it as expectation of y given on x. Given on is denoted by a slash. Why? Because as you can see here that that mean is calculated from the total of 325. Now, is this total being calculated from all the 15 families, or is this total being calculated from all the 15 values of 15 family consumption expenditures? Not at all. This total is being calculated from only those 5 families who are having the income of $80. This total is being calculated from those only 5 values, or only 5 families who were under the income group of $80. Okay, so that's why we can say that this expectation of y, or this mean of y, is depending upon x. It is depending upon the condition of x. That's why we are calling it as expectation of y given on x, or we can also name it as conditional expectation. Similarly, for the second group, it is also the conditional expectation, that is 72. For the third group, it is also the conditional expectation, that is 100. Right? So that is the second assumption, that is x values are fixed in repeated sampling. Now we are going to the next assumption. You can just check in this. You can read this if you are interested. Then if we have a fixed values of x and y, corresponding y values against each of the x values, we can call these mean values as conditional expected values, as I have told, as they depend on given values of the variable x. We denote them as expectation of y given on x, which is read as the expected values of y given on the value of x. Then what is the unconditional expected value of weekly consumption expenditure? Well, that is very easy. Unconditional expected value means you have to add the 15 values of all the families, all of the consumption expenditure of all of the families, and then we have to divide it by 15. Okay, so as we have done here also, let me just show it so that you understand it. So this is unconditional expectation, unconditional expected value, which is denoted by expectation of y, which is 85.8. We have added 15 values here, all the 15 consumption expenditures, and then we have divided it by 15. Okay, so this is the concept. Third assumption that is important here, that tells us that we have discussed about the error term in the previous class. The error term takes all the factors which can impact or which can affect the dependent variable. We can take an example in today's class also, that suppose demand depends upon price. Now, does demand only depend upon price? Is there no other factor that can affect demand? If I am writing an equation that demand equals to alpha minus beta p, does demand only affected by price? No, demand is affected by multiple other factors like income, price of related commodity. There are multiple other factors which can affect demand, right? But we are not taking those factors into our model, so our model will be inaccurate. So that's why for taking or for considering all of those other factors that can affect demand, we are adding a error term in our model, that is referred as random error term, which is denoted by ui or sometimes epsilon I also. Okay. Now the third assumption is about this error term. What is the third assumption telling? That the error term has zero mean value. Okay. Now how can we explain this? Zero mean value, or this is a conditional mean. Okay, this is depending upon xi. This mean is depending upon xi. This mean of error term is depending upon xi, and the conditional expectation of the error term is 0. Now how can you define it? As I have told in the previous class, you must watch that previous class. I will persist that when we take the x on the x-axis and take the y on the y-axis, and we plot the data points by the help of scatter plot, we get multiple points. From those points, we basically create a best fit line. What is the criteria that we follow for creating that best fit line? That best fit line has the minimum distance from all the points. Okay, so suppose this is let me just draw it here. Suppose this is our x and this is our y, right? Now there are multiple scatter plots, scatter points that are being here. Now this can be a line, this can be a line, and this can be also a line. There can be multiple lines you can draw, but which line will you select as the best fit line? The line has the minimum distance from all the points. That line we will select as the best fit line. Okay, now these points which are not present on the line, there are multiple points that are actually present on the line, right? That's why this line is being created, but there are other points also which are not on this line. These points are referred as error terms. Okay, these points are referred as error terms. Now as you can see, the error terms, these are error terms. These error terms, it is not like that the error terms are very much spreaded from the best fit line. The error term, suppose if I take the example of this error term, suppose the error terms are situated like this. Thus these couple of error terms are very far away and these error terms are very close. This is not the case. If this was the case, then we can't say that the expectation of the error term is 0. Here what is happening, the error terms are very closely situated. What am I telling here? The error terms are very closely situated. So error terms are very closely situated and they are equally spreaded on the both sides of the line. So if you take the expectation of the error terms, what is the distance of the error terms on the positive side? That is plus ui. And what is the distance of the error terms on the negative side? That is minus ui. So if you take the calculate the mean of the error terms, that will be plus ui minus mu, that will be divided by 2, that will be equals to 0 by 2. So it will be equals to 0. So that's how you can actually explain that the error terms are equally spreaded on the both sides of the best fit line. So whenever we try to explain the mean or conditional expectation of the error term, that will be always 0 because they are equally spreaded on the both sides of the best fit line. So this is the concept of the fourth assumption probably. Let me just, this is fourth or what? You may just read it also, that will be very helpful for all of you. Let me just go in the fourth assumption, that is homoscedasticity. It is also associated with the previous figure that was being shown. Homoscedasticity tells that error term is equally spreaded. Error term is equally spreaded from the best fit line. It has the equal variance. It will never happen that suppose this is the best fit line and some error terms are very far away, some error terms are close. This type of situation can never happen. This type of situation is, if this type of situation happens, then we will say that assumption is violated. But what is happening? The thing that is happening here, that is, let me just draw it. The error terms are equally spreaded on both sides of the regression line or both sides of the best fit line. So that means error terms have the equal variance on both sides of the regression line or best fit line. This assumption called homoscedasticity or equal variance of the error term. Okay, given the value of xi, the variance of ui is same for the all observations. So that means homoscedasticity or equal variance of ui means that all the values of given the values of xi, all the error terms, all the ui have the equal variance. Okay, it can be denoted as variance of ui given on xi. It is conditional variance. We are always dealing with conditional variance, conditional mean, okay, conditional expectation in case of these assumptions. I hope these terms are new for you, but it is the case in case of the assumptions of CLRF. Variance is what? Variance is expectation of ui minus expectation of ui given on xi whole square. This term is nothing but 0. We have done it in the previous assumption, that was assumption 3, that this term is 0. So we will have only expectation of ui square, right? And obviously it is depending upon xi. It should be here also, you can add xi, so that this xi doesn't look like that it is jumping out of nowhere. This is not the case. Here xi was present with ui also. Okay, this ui was also conditional upon xi. So this is expectation of ui square given on xi. This is referred as sigma square. What is sigma square denoting here? Sigma square is denoting that variances of the error terms are equal. Variances of all the error terms is equal. Okay, and error term does not have an unequal variance. If error terms have unequal variance, then that is a violation of the assumption, and that violation of the assumption is called heteroscedasticity. In that case, everything will be same, just we will write sigma I square here. Okay, and the remaining things will be same, and this will be turned out heteroscedasticity or unequal variance in that case. Okay, so this is the fourth assumption. You may read it for some better intuition. Next is we are going to take, here it is, heteroscedasticity assumption is also given. You guys can read it. Okay, I am going to tell the fifth assumption. Fifth assumption tells that if there are two x values, and with respective to those two x values we have two different error terms. Okay, then these two different error terms have no correlation in between them. More specifically, we can say it as, suppose I have an error term of this period, that is current period, and I have an error term of the previous period. Then these two error terms have no correlation, in between them. I can take an example of this. Suppose India played very bad today, or India played very bad yesterday, but it has no correlation with how India will play today. Right, I am talking about the cricket team of India, that it has no correlation that how India will play tomorrow or today. India has played bad today, India has played bad yesterday, that I am accepting, but it has no correlation with how India will play today. So that means these two have no correlation. This is another assumption of the error terms. Okay, that there is no correlation between the disturbances, and it can be further written as covariance of ui uj given on xi and xj. Ui given on xi, uj given on xj. Okay, this can be further break down as in the formula of covariance, and this can be written as 0. If correlation is 0, that means covariance will be always 0, because correlation, the formula of correlation is nothing but covariance divided by sigma of x into sigma of y. Correlation is nothing but covariance of xy divided by sigma of x and sigma of into sigma of y. Right? So if this part is 0, then correlation has to be 0. So that's why we explain it by this part, that is the part of covariance. So I hope this is clear. Now we are going to the next assumption. So the next assumption, this is the concept of correlation. You can see from here that if they are positively correlated, the error terms, then this type of graph will be shown, and if they are negatively correlated, then this type of graph will be shown. For positive correlation, this type of graph will be shown. For negative correlation, the error terms will have this type of graph, and for no correlation, this type of graph will be shown. Okay, and the next assumption, before going into the next assumption, is this is the next assumption that tells us that zero covariances between the error term and the xi. We can also explain it in this way, that there is no relation between the error term and the independent variable. Well, that is very honest to be said. That means independent variable is completely independent of other factors. Yi, that is our dependent variable, it has it is depending on error term. How? Because error terms is what? Error terms is all those factors which are affecting yi except xi. Except xi, all those factors which are affecting yi are included in error term. So yi is depending upon error term, right? But what about xi? Is it depending upon yi? Is it depending upon error term? Obviously no. So I can say that there is no correlation between xi and error term. And as I have said, if there is no correlation, if correlation is 0, that means covariance has to be 0. So I have to say that there is 0 covariance between error term and xi. Okay, mathematically you can show it here also. So this is the concept of 0 covariance. This is the 6th assumption. 7th assumption is that the number of observations must be greater than the number of parameters to be estimated. Suppose I have some values of x and y. I have only one or suppose two value of x, y, 10, 5, 7, 3. Okay. And I have given the equation that is y equals to alpha plus beta xi. Now here how many parameters I have to estimate from here? There are two parameters here that I have to estimate. One is alpha, one is beta. How many pairs of observation is given to me? Only 2 pairs of observation is given to me. If this is the case, we won't be able to estimate the parameters. That is a limitation here. So how many observations should have been given? At least 3 pairs of observations should have been given to calculate the parameters. This is the 7th assumption. Let me see if it is done. Yes, it is done. And we are going to the last page. This is the 8th assumption. It tells that x values in a sample must be different. Obviously x values were different in a sample, right? X values were never same. Okay, if x values are same, then what happens? The mean of x becomes equals to x values, right? Suppose if I take the example, suppose we have different values. Suppose x values are same, 20, 20, 20. You will calculate the mean, it will be also 20. I haven't discussed this part of the formula, but I have derived the formula, but I haven't discussed the intuition behind or mathematical purpose or numerical way of defining it. So I am not going to explanation of this. But if just know this part, that if x values are same, then their mean will be also same, and the difference of x values with their mean, which is required, difference of x values with their mean which is required in the calculation of beta hat, which is a slope parameter, also becomes 0. So the beta hat will also become 0. So that's why x values should be variable. That means x values should change. X values should not be same. Okay, 1 or 2 x values can be same, but not all. All the x values can't be same. 9th assumption is the regression model is correctly specified. That means correctly specified means suppose there is a non-linear regression model, but you have fitted a linear regression model in that case, then that is misspecification of the model, right? So regression model has to be correctly specified. If the regression model is non-linear, then you have to specify it as non-linear. If the regression model is linear, you have to specify it as linear. But if the regression model is linear and you are fitting it as non-linear, then that is misspecification of the model. And the 10th assumption is there is no perfect multicollinearity. Perfect multicollinearity means the independent variables should not have any relationship between them. Suppose I am taking an example. Suppose y equals to y is nothing but consumption. Okay, y is depending upon suppose beta x1 plus gamma x2. Here this x1 is income, x2 is saving. Now consumption is depending upon income and saving, that is okay. But well, think about it that x1 and x2 are income and savings. These two are the independent variables, and these two independent variables, income and saving, have a relationship in between them, right? Income and savings are completely related with each other. If my income increases, my savings will increase because savings depends on income. If my income decreases, saving will decrease because saving depends upon income. So income and savings are completely related with each other. So that means there is a relationship between independent variables, right? So when there is a relationship between the independent variables, we are calling it a problem of multicollinearity. Okay? And when this multicollinearity is there, that means you can't specify it as a linear regression model. Your assumption will be violated. If these 10 assumptions are correctly ticked, then a model of the form of, suppose this form, y equals to alpha plus, I am taking a very simple form, xi plus, okay, I am just writing here in a little bit better handwriting probably, alpha plus beta xi plus ui. A model of this form, it can also have more than one independent variable, but a model of this form can be termed as classical linear regression model if all of the 10 assumptions are satisfied. Okay.